Hello everyone, I am Dr. Shubhra Mishra from the Department of Physics at Government Naveen College, Gudihari, Raipur. In today's lecture, we are going to discuss the topic of dielectric as part of our course on Fundamental of Engineering Physics. First, we shall start with an introduction to dielectric. We will define what dielectric are and why they are crucial in various applications, particularly in electrical and electronics engineering. Next, we will move on to the classification of dielectric. Then, we will explore how dielectric can be categorized based on their properties and behavior under different conditions. Following that, we will discuss dielectric properties. Here, we will look at key properties such as dielectric constant, dielectric strength, and understand how these properties influence the performance of dielectric materials. We will then explore into the polarization of dielectric, different types of polarization mechanism including electronic, ionic and orientational polarization. After that, we will cover the dielectric constant and its significance. Then, we will understand what the dielectric constant is and how it is affect the storage of electrical energy in capacitor. We will also look at the types of dielectric materials. We will explore some examples such as ceramic, glass, polymers and discuss their application. Then we will discuss dielectric breakdown. We will understand the conditions under which dielectric fails. First of all, dielectric are material that do not conduct electricity, but can support an electrostatic field. This means they can store and separate electrical charges. First, we will talk about the classification of dielectric. Dielectric can be divided into two types. First one is polar and another one is non-polar dielectric. Polar dielectric have molecules with a positive and negative end like tiny magnets, and non-polar dielectrics do not have this, but they can still become polarized when we apply an electric field. In polar dielectric, here the diagram shows the behavior of non-polar and polar dielectric material in the presence and absence of an external electric field. Molecules have a permanent electric dipole. This is the example of water. This means that there is an inherent separation of positive and negative charges within each molecule, even in the absence of an external electric field. In non-polar dielectric, here diagram shows molecules do not have a permanent dipole moment. For example, nitrogen. In this material, the positive and negative charges are symmetrically distributed and there is no net dipole moment when there is no external electric field. Dielectric properties refer to a material's capability to store and separate electrical charges when electric field is applied. Key properties include the dielectric constant, which measures how much electrical energy the material can store, and the dielectric strength is the maximum electric field a material can handle without breaking down. Now, we discuss some different dielectric properties. First is insulating properties. What is insulating property? Dielectric are insulator means they do not conduct electric current. This property makes them ideal for use in insulating electrical components and preventing short circuits. Then next property is polarization. What is polarization? When an electric field is applied to a dielectric material, the electric charges within the material are slightly displaced from their equilibrium positions. This displacement creates an internal electric field that opposes the external field, and this phenomena is known as polarization. Next topic is dielectric constant. Dielectric constant is a measure of materials ability to store electrical energy in an electric field. Actually, dielectric constant is defined as the ratio of the permittivity of the material, which shown from epsilon, to the permittivity of free space, which shown from epsilon naught, and higher dielectric constant values indicate a greater ability to store electrical energy. And what is electrical susceptibility? Electrical susceptibility property defines how easily a material can be polarized by an external electric field. Next topic is breakdown voltage. The maximum electric field a dielectric material can withstand without breaking down means losing its insulating property is called the breakdown voltage. Beyond this voltage, the material becomes conductive. Polarization of dielectric. Here, figure explain the electric polarization. In this diagram, on the left side, without an external electric field, the charges in the dielectric are randomly oriented, and on the right hand side, with an external electric field, the charges align, showing induced dipoles with positive and negative charges separated, and this is oriented according to the field. Polarization means if a dielectric is subjected to an external electric field, the electrically charged particles undergo displacement and ordering in space, causing the formation of electric dipole moment in the whole volume of the dielectric and each separate polarizing particle. In the case of linear dielectric, the electric dipole moment is directly proportional to the intensity of applied electric field. Here, applied electric field denotes from capital E. So, P is proportional to E, or P equals to alpha E, where the proportionality coefficient is known as polarizability of the molecule, as the polarizability reflects the property of an individual particle. It is very important microscopic electrical parameter of the dielectric. The dipole moment per unit volume is known as a polarization. The electric dipole moment may also be expressed as the product of the charge and the distance between the two charges of equal magnitude, but opposite polarities, as shown in here figure. In this figure, A is the distance between two charges and E is the charges. So, P equals to AE. Dipole moment is a vector quantity pointing from negative charge to the positive charge, and the unit of dipole moment is dBi. 1 dBi equals to, we know that 3.33 into 10 to the power minus 30 centimeter. Next topic, mechanism of polarization in dielectric. Polarization in dielectric happens when an electric field causes the charges within the material to align in a specific direction. There are different ways this alignment can occur, and this depending on the type of dielectric material. Let we explore the main type of polarization mechanism. There are three types of polarization mechanism. First one is electronic polarization, second one is ionic polarization, and third one is orientational polarization. What is electronic polarization? In this mechanism, the electric field causes the electron clouds in atom to shift relative to the nucleus, creating a dipole moment. This is a rapid process and occur almost instantaneously when the field is applied. Here the diagram shows to represent a crystal lattice structure with a focus on the magnetic or electronic properties of the material. This is the 3D diagram of atoms. This diagram shows electronic properties such as the distribution of electrons in different energy bands. Second one is ionic polarization. This is the colorful diagram, and this diagram shows a grid of atoms with positive and negative charges. When an electric field is applied, here electric field is shown by the arrows. The positive and the negative charges shift slightly. The positive charges move towards the direction of the arrows, and the negative charges move the opposite direction. This shifting creates a situation called polarization, where the charges are lined up in a way that makes the material better at handling electric fields. This occurs in materials where there are positive and negative atoms or ions. When an electric field is applied, these ions are displaced in opposite direction, and this create a dipole moment. And third one is orientational polarization. In polar dielectric, the molecules have permanent dipole moments. When an electric field is applied, these dipoles tend to align with the field and enhancing the polarization effect. In most dielectric material, all three types of polarization can occur simultaneously, contributing to the overall polarization of the material. The total polarization is the sum of all polarization contribution from electronic, ionic and orientational polarization. Understanding the mechanism of polarization actually helps in designing material with desired dielectric properties for various applications such as insulators, capacitors and other electronic components. What is dielectric constant? Here the diagram shows how a dielectric material means insulating material, behaves when placed between two charge plate. Left side, when there is no dielectric material, the electric field between the plate is strong, and this is shown by many red arrows going straight up from the positive plate to the negative plate. The positive and negative charges are far apart, indicating a strong electric field, and right hand side, when a dielectric material is inserted between the plates, the electric field is reduced and shown by fewer and smaller blue arrows. The dielectric material causes the positive and negative charges within it to shift slightly, which creates internal fields that oppose the external field. This results in the overall electric field being weaker compared to the situation without the dielectric, and this is the 3D diagram of dielectric constant. Actually, dielectric is characterized by its dielectric constant epsilon r, which is also called relative permittivity. The basic electrical phenomena that occur in dielectric material can be understood if we consider a solid dielectric located in the region between the plates of a parallel plate capacitor. The dielectric constant is defined as the ratio of the permittivity of the dielectric material to the permittivity of free space. The dielectric constant is measure of material's ability to store the electrical energy in an electric field. It is defined as the ratio of epsilon upon epsilon naught. Mathematically, here epsilon r equals to epsilon by epsilon naught. A higher dielectric constant indicates a greater ability to store electrical energy, which is particularly important for capacitors. And the second figure shows the parallel plate capacitor connected to the DC volt source V naught. The voltage source charges the capacitor plate till the potential difference across the plates built to V naught. Assume the charges on the plates will be plus Q naught and minus Q naught, and the difference between potential difference between is V. The capacitance C naught is selected to the quantity of charge stored on either plate, and suppose we assume the plates of the capacitor be disconnected from the voltage source V naught. The circuit is open now and there is no path through which energy can flow out or flow in from the system. So, the magnitude of charge Q naught on either plate must remain constant. Now, consider a dielectric in the form of a rectangular parallel pipe is inserted between the plates and it must completely fill the space between the plates. Due to this, it is found that the potential difference V naught decreases to a value V as shown in here the figure. If the dielectric slab is pulled out, the potential difference returns to the original value of V naught. This experimental fact processes that the original charges on the plates and it can be concluded that the value of the capacitance increase from C naught to C in the presence of the dielectric. So, epsilon r is a dimensional quantity which is always greater than unity in case of dielectric and it is independent of the size or shape of the dielectric. It is called dielectric constant or relative permittivity. Here we observe the charge storing capacity of a capacitor is enhanced by the dielectric which permits it to store n times more charge for the same potential difference. The general method of determining the dielectric constant of a dielectric is to measure and compare the capacitance of a capacitor containing the dielectric medium to the capacitance of the same capacitor with air as the medium. These are the mathematical derivation and what is the significance of dielectric constant. First, energy storage. A higher dielectric constant indicate a greater ability to store electrical energy. This is crucial for the efficiency and capacity of capacitor. And second one is the capacitance. The capacitance of capacitor is directly proportional to the dielectric constant of the material between its plates. Types of dielectric material: solid dielectric, liquid dielectric and gaseous dielectric. There are three types of solid dielectric material. The first one is elemental solid dielectric. Solid dielectric materials consisting of a single type of atoms such as a diamond, sulfur, germanium. Ionic nonpolar solid dielectric. In ionic crystal such as alkali halide, the total polarization is ionic and electronic in nature. These solids contain more than one type of atoms, but no permanent dipoles. This type of dielectric material are said to be ionic nonpolar dielectric material, and the third one is polar solid dielectric material. In solid whose molecule possess permanent dipole moments, the total polarization has all the three components. It is the sum of electronic polarization, ionic polarization and orientational polarization. This type of material are known as polar solid dielectric. For example, solid C6H5NO2. What is liquid dielectric material? There are also classified in three types. First one is mineral insulating oil, second synthetic insulating oils and third one is miscellaneous insulating oils. Mineral insulating oils means transformer oil, capacitor oil and cable oil are said to be mineral insulating oils. They are directly obtained from crude petroleum by distillation. They are used as coolant in transformers and capacitor. And synthetic insulating oil means synthetic insulating oils are also used for the purpose of cooling in high tension transformers compared to mineral insulating oils, synthetic oils, and they are very cheap. Miscellaneous insulating oils, silicon liquid and vegetable oils are said to be miscellaneous insulating oils. The silicon liquid is costly compared to synthetic insulating oil. It is used in high tension transformer. Applications are actually petroleum oils are used for electrical insulation, and nowadays synthetic hydrocarbon oils are replacing minerals insulating oils. Polychlorinated biphenyl is also used for non-flammable insulation in transformers and capacitors, but they are being phased out due to pollution. Silicon liquids are now used instead for non-flammable insulation. In developing countries, castor oil is used as an insulating liquid. Gaseous dielectric material, air, nitrogen, hydrogen are some of the gaseous dielectric material. Air is the one of the most important and naturally available gas used for electrically insulation. Its resistivity is infinity under normal conditions when there is no ionization. The relative permittivity of air is 1. It is used as a dielectric in long distance electrical transmission and in air capacitor. Compressed air is used as an extinguishing medium which provides dielectric insulation in air blast circuit breakers. Nitrogen is chemically inert and is used as a dielectric medium to prevent oxidation. It is used in gas field high voltage capable as an inert medium to replace air in the space above the oil. It is also used in transformer and in low loss capacitor for high voltage testing and so on. Next topic is dielectric breakdown. Dielectric breakdown occurs when an insulating material is subjected to high electric field. This phenomena typically happens when the electric field exceeds the material's dielectric strength, leading to the rapid formation of conductive path and resulting in electrical discharge. Dielectric breakdown can damage the material and associated electronic component, making it is a critical factor in the design. Mechanism of dielectric breakdown: initial state, applied electric field, avalanche effect, conductive path formation, electrical discharge. What is initial state? The dielectric material resists electrical conduction due to its insulating property, and applied electric field is the field increases electrons in the dielectric material gain energy. What is conductive path formation? The rapid increases in free electron results in the formation of conductive path through the material. There are different applications of dielectric. Capacitor are used, dielectric are used as the insulating material between the plates of capacitor. Insulator, dielectric are used to insulate electrical wires and components, preventing short circuits and ensuring safe in electrical system. Material like rubber, plastic and ceramic are commonly used dielectric for insulation purpose. Some other application of dielectrics are quartz crystal. Quartz crystal is used for preparation of ultrasonic transducer, crystal oscillator, etc. We use barium titanate for preparation of accelerometer. Insulating dielectric liquid are used in switch gears. So, dielectric material are used as insulating material in power cables, signal cables, electric motors and other electric devices. Now, we can summarize the entire topic as dielectric are crucial material in the field of electrical and electronics engineering. They are insulators that support an electrostatic field and are used extensively in devices such as capacitor and transformers. Understanding their properties, classification and application help us appreciate the role in modern technology. Dielectric are classified polar, non-polar. Dielectric enhance the capacitance of energy storage of capacitor, making them essential for power supplying, and the application of dielectric material is crucial for advancing modern electronic and communication technology, and this is efficient for a wide range of devices and systems. These are the references. Thank you for your kind attention.